Okay. Okay, so Martin is going to tell us about timing reionization with Lyman-alpha in emission and absorption, and I will give him the indication you might see it, but we've got 5 minutes to go.
Is that better? Okay. So as you go to higher and higher redshift, what you see there is that the Lyman-alpha force becomes thicker, and neutral hydrogen is very sensitive to probe of ionizing radiation, and even if you have a very small neutral fraction, you get a very large optical depth. And for a long while, we didn't know how to interpret these spectra very well. These spectra were around for 20 years maybe before we really figured out that actually the end of reionization was staring us in the face in these spectra. So as you go to higher and higher redshift, you get higher optical depths, and you get then damping wings that go to the red side. And but if you look at redshift 5 and 5 to 6 spectra, what you see that there's a large variation from object to object. And the main information is actually in the scatter between line of sight to line of sight. So there are some lines of sight where you still have quite a little bit of transmissions that are obviously highly ionized, but there are also lines of sight that show these long gone Peterson troughs. And as we figured out painstakingly, maybe in the last 10 years, these are actually the signs that there is still neutral gas that's not stretching over the full length, but they're neutral islands that makes this much more neutral than in this island, than in this line of sight here. And by looking at this statistically, you could actually figure out that the reionization ends between redshift 5 and 6. This is sort of what happened over the last 5 years or so, that we moved from models, sort of the last neutral islands were disappearing at a redshift of 6 to models where you still have substantial amounts of neutral gas that last down to redshift 5.5, 5.3. And then we use this to get a larger number of spectra. This was a project driven by a student of mine, of Sarah Bosman, and a student of mine and George Becker, together with Valentina Puerto Rico. We got a large sample of X-shooter spectra to measure actually these scatter in the optical depths as you go to higher redshift with very high accuracy, so that you could actually hear very good PDFs. And this is a very good measure about how reionization ends, and we moved sort of the epoch where reionization ends from 6 to nearly to redshift 5. This is some of the papers that we got out of this program. And then the next question is what are actually the sources that do the reionization? And before JWST, AGN had fallen out of favor for making a significant contribution to reionization, mainly because just adding up the ionizing photons, you found that there weren't enough of them to do this. But there's another problem if you do too much reionization with AGN, is that AGNs have much harder spectrum, and they can actually ionize helium to the second ionization state, so that everything is in helium-3. this leads to an extra energy input which heats the IGM to temperatures that are larger than observed. So pre-JWST, AGN has actually fallen out of favor as being a significant source of ionization. We have reconsidered this a little bit after JWST in light of the many black holes that JWST found, but the conclusion basically hasn't changed. So before this, I think your local colleague Piero Madao, he sort of every 10 years he writes a paper, could ionization be due to AGN only? In the end, I think the next one is probably due in 7 years or so. At the moment, as it looks like, even though there are many AGN, for the same reasons that I've actually discussed, they're probably not producing enough photons to contribute fully. The problem that they would lead to too high temperature of the IGM hasn't gone away. And there's sort of a new problem that if the sources of ionization are too rare and are too sort of intermittent, then the distribution of the flux, how ionization ends, doesn't fit anymore either. So I've looked into this with a recent student of mine, Shika Astana et al., where we did detailed simulations of ionization where AGN is either done completely, where ionization is either done completely by AGN or it's done by QSO-assisted model where 10% of the ionization is ionizing photons comes through AGN. And we found that even these 10% of AGN producing the photons lead to a significantly different distribution of the flux that is not consistent with what you observe. So QSO only is really not working, and even sort of the AGN contributing, I think you can probably limit this contribution to about 10 or 20%. So the other thing what has changed with JWST is that it seems that ionization seems to, even though it ends very late, probably starts quite early. So it's a very extended process. So we have run in this paper with Shika Astana models where we artificially put sources at very high redshift so that ionization sort of starts much earlier. And this was mainly to sort of cater for the observations that you see actually Lyman-alpha emitters out to very high redshift. And the highest redshift that we have seen in Lyman-alpha emitter seems to be at a redshift of 13, which is a truly remarkable object because you see a real whopping Lyman-alpha line at redshift 13, even though you would expect that due to the damping wing of the noodle gas in front of this, it should be rather unlikely. So there is now sort of the discussion if you have models where these models are all calibrated the same way, that they fit the Lyman-alpha forest at redshift 5 to 6, and they sort of start at different times, and you see they're quite different in terms of how large ionized bubbles are early on. And this discussion, I think, will become more lively, and I think in light of the talks that we've just heard, I think with these very small escape fractions that don't rise early on, it would be difficult to get a model like this here. You really have to have higher escape fraction in the area here. The reason why this becomes interesting is because we can now model this in detail. So there will be Lyman-alpha emitter surveys that go to higher and higher redshifts, and we've looked into this, and I think the one thing that we found is that the Lyman-alpha emitters are very highly biased, like all high redshift galaxies. So this helps you a little bit with actually having the galaxies in the bubbles. The bubbles are where the galaxies are, and therefore, even though the universe isn't as ionized at that time, where the galaxies are, you normally actually have a bubble. So this helps a little bit with finding these many Lyman-alpha emitters at high redshift. Another thing what helps is that probably the intrinsic Lyman-alpha emission is changing quite a lot. The one thing you have to assume when you model how the Lyman-alpha emitters disappear due to the intervening opacity of the noodle gas is that you have to assume where in redshift actually the intrinsic Lyman-alpha emission sits. And this can easily evolve if you have galaxies that have outflows, and a lot of noodle gas in the outflows that can shift actually the line towards the red, and this helps to avoid the damping ring that sits in front of the gas. This is what Jux and Jörn, another student of mine, has looked into a very nice formulation from Sergio that we will hear more about on Friday from. And what he found is that you can have very extended red wings in these outflows that avoids the damping wings. And this helps also with making these galaxies more visible at high redshift. This is sort of a detailed looking at how the peak of the redshift evolves with redshift and how the equivalent width evolves with redshift. The other interesting thing is that we probably can now map out the ionization history very well from this effect that the damping ring on the red side becomes more and more prominent as the gas becomes more neutral. There's been a nice sequence of papers from the Japanese group led by Hiroshi Yumida. It's the first paper that came out a bit more than a year ago. There was another one earlier this year, just a couple of months ago, where they see very clearly that these red damping wings in stacked spectra become much more prominent as you go to higher redshift. Turning this into a measurement of the overall volume filling factor of noodle gas is difficult, mainly because there's also damping wings due to the interstellar medium into the galaxies, and you have to disentangle the two. But there's now so many high quality spectra that I'm quite confident that sort of over the next 5 years or so you will be able to disentangle the two. You will actually be able to get a nice mapped out noodle volume filling factor as a function of redshift. This is from the corresponding modeling paper of a former student of mine, Laura Keating, who has actually modeled this in some detail. The other thing that has been very interesting in the last few months is that in the ionization community, the Planck optical depth from 2018 has been sort of always considered as being written in stone. It's something what's well measured. And the Planck optical depth is actually rather low. If you actually talk to the people who have produced this, like George Eftasio, they will tell you that the optical depth is the one quantity that the CMP actually doesn't measure very well. You can measure this from the temperature power spectrum, you can measure this from the polarization power spectrum. Neither of them is measured very well. And everybody who has sort of interacted with George knows that he's very possessive of the Planck data and would be very careful to sort of go in and to think what's published there. But this is the one quantity where you can actually assume that the errors are probably widely underestimated. And the cosmology community has actually realized that these Planck optical depths causes problems with other cosmological parameters. So for example, with improved data, people found that the neutrino masses that you were inferring were suddenly starting to become negative. It's obviously not physical, just meant there's actually an uptick in the power spectrum where you would see a suppression of this. So there was a sequence of papers that have actually explored the possibility of what happens if you assume a much larger optical depth, even larger up to a factor of 2 or so. And this helped both with, for example, the neutrino masses and the discrepancy of the early dark energies and the evolving dark energies that Risa has discussed this morning. The significance of this measurement goes significantly down with this too. So I think what should happen here is that the CMB community is sort of still hung up on models where they have these tonnage models where you have a width of the model and have a sort of a ionization redshift. I think as we have fixed now the end of ionization, you should actually go to models that all end and get the Lyman-alpha force right. They can have earlier ionization by just shifting the midpoint. And this might actually solve a lot of problems. And I think the point I want to make here for the people who are not working in this field is that at the moment there's a lot of sociology involved, but at the moment it moves away from the Planck optical depths to larger values and earlier ionization, which becomes then a problem, say small escape fractions that we heard about in the first talk of the session. So here's a summary of possible reionization histories from the paper from Schicker that I showed earlier, where you see here's the optical depths and here's a green model, is a model that maybe was favored 2 or 3 years ago with the Planck optical depths. The measurements that we have from JWST are still all over the place. The model with early reionization, what would help a lot with early Lyman-alpha emitters, is sort of this green model where you get here to an optical depth that is more like twice the Planck value. I would think sort of a compromise model is sort of somewhere in the middle, like the Brown model here, which probably satisfies everybody, helps a little bit with the neutrino masses, and also helps with reducing the significance of the early of the evolving dark energy. So here you have my summary in terms of reionization. I think over the last 5 to 10 years, I think we have established that reionization actually ends rather late. That you have nodal hydrogen that lasts down to redshift of at least probably 5.2 or so. You see damping wings even at these low redshifts from diffuse gas. I think George Becker actually in the spectrum of one of the long troughs, he actually has convinced himself that on the sides there's a damping wing as well. As you go to higher redshift, you see now damping wings all over. I think I have in my career worked a lot of DLAs at redshift 3 or so, where damping wings were exclusively from interstellar medium and galaxies. I think now we're seeing sort of damping wings for more diffuse gas everywhere at high redshift. And with this large number of JWST spectra, we should actually turn the thing around and not let the CMB tell us anymore what the reionization optical depth should be. I think the community and JWST should actually be able to provide an integral over what the neutral fraction is by using all the information of these wonderful spectra. The Lyman-alpha emitters are found at surprisingly large redshifts. So there's also very bright galaxies. So I think there is a reason to believe that action happens actually very early in lambda CDM because star formation becomes efficient. It's probably the small galaxies where the photons come out. And then you can have a very extended reionization period where you actually start early and finish late. And on this, I want to finish here as well.
So thank you very much for keeping well on time there. We have time for a number of questions.
The more extended reionization history, is that, if you want to model that, is that sort of hinting at maybe there have been two populations of reionizing sources that show up at different times? Or
you can entertain models like this as well. As you know, in large optical depths was what we started with from the CMB. I think WMAP first year data, it's this optical depths of 0.12. And then the model mini AGN, so you can certainly entertain models again where you have some early thing galaxies being very efficient starting early. So that you have the bubbles, so that the Lyman-alpha emitters have already larger bubbles to sit in. If you really have to go all the way to twice the Planck optical depths, I don't know. But I think this community has always taken this as written in stone, and I think you should really drop this, because even the cosmologists don't hanging on to this anymore.
By the way, is Pablo here? We're ready to get. Could be setting up during the next question. Okay, next question. Garth.
Yeah, thank you. Thanks, Martin. So one question I had was, my memory is that the Planck folks were saying from after their analysis that no more than 10% before redshift 10. So reconciling that with what you were commenting on here and what we're seeing from JWSC seems a little challenging. Is there something about the Planck results that may need some revision?
The Planck was never meant to measure polarization. So this is a statistical error. And in the Planck paper, there was actually a mistake in the model as well. So I don't think you should take this seriously. This might just be a systematic. And can be not jump to if you claim they might be systematic, and it might be just systematically off.
One last short question from David there.
But in fact, we see cosmic webs, and so I'm wondering, given that the pool of ionizers might actually be the low mass galaxies, they might be following more of a web-like structure rather than bubble structure. Did that matter at all?
The topology is actually very similar no matter what the sources are. And the reason for this is galaxies are very biased at high redshift. Once you go beyond redshift 6, low mass galaxies also sit in halos that have at least a dark matter halo mass of 10 to the 9. 9 solar masses, halos cluster together with the 10 to the 12 solar mass halos. So the topology is actually sort of disappointingly similar for the small mass galaxies and for the bright galaxies. There's subtle differences, and the first halos cannot be so large, but if you make sense the galaxies brighter in the small halos, then you really don't see a difference. So it will be very hard to find out the sources. For this, you probably have to go for looking at the cross correlation between the spectra and the sources, and you can do this now. And there are large number to do this, and Eiger is one who has very large, nice data on this, but there will be more and more on this. And to disentangle in the two is possible, but needs very careful work because they're actually not that different. And the reason being that everything is very highly bound.
Okay, well, let's thank Martin again. And now we're going to move on to Pablo. I'll wait. I think we got 5 minutes to go.